Hi, today we're talking about VSEPR theory. Although nobody ever calls it whatever that was, we just pronounce it as VSEPR, even though it doesn't really look like it should be pronounced that. That's what we call it. Now this is going to be a two-part video. The first part is going to be an introduction and get an idea of some basic things, and then the second part will be filling in some of the blanks that we leave out in the first one. So hopefully this is brief, but honestly I've learned that every time I say this will be a brief video, it's never a brief video. But it stands for valence shell electron pair repulsion theory. And you might be wondering what that means, but if you think about it, the valence shell just means the outer electrons, and those are involved in all the chemistry, all the bonding. So we have bonding electrons, and then repulsion. Well, and then the theory that, well, okay, let's just get on with it. So like charges repel. That's one of the fundamental things that you know about in science. Electrons all have a negative charge, they're going to be repelling. Bonds have electrons, so that means that the electrons in those bonds won't necessarily be repelling each other, but they might be repelling electrons in other bonds. And central atoms, they also might have lone pairs of electrons, electron pairs that are not involved in bonding. And you remember from drawing Lewis diagrams that one of the last rules was to put remaining pairs of electrons on the central atom. So we may have non-bonding electrons on the central atom. And then as they all repel each other to try and get as far away from each other as possible, that's going to influence the overall shape of the molecule. So that's really what VSEPR theory is all about, trying to figure out the shape of a molecule from its Lewis diagram. Now there are a couple of things that we'll have to keep in mind, not so much for right now, but as we move forward and as we try and put this into practice, and as we take Lewis diagrams and say, yes, this is what the shape is going to be. Number one of them is that different types of electrons repel each other in different ways. So two pairs of lone pairs are going to repel each other very, very strongly. Lone pairs will then repel bonding pairs strongly, but not as strongly. And then finally, bonding pairs to bonding pairs, that's the weakest repulsion. So they're still going to repel each other. But if you have to decide between putting a lone pair as far away from everything else as possible compared to a bonding pair, lone pair is going to be repelling much more strongly than the other types. And then finally, we have to revisit our concept, not revisit, we have to remember our concept of an orbital, where an orbital is simply a place where you are likely to find an electron. And as other factors start to come into this thing, like repulsions by electrons, where you're likely to find that electron might actually change. So we have to be a little bit more flexible in where we put our electrons, or where we're willing to put our orbitals, or what we're willing to think an orbital looks like. Okay, but again, that'll come out as we get into some of the other details of this. Other thing is that a multiple bond will actually behave as a one bonding group. And one of the things that we kind of get into trouble with is, not trouble, but when you talk about bonding groups or pairs of electrons and things like that, we start to get a little bit, well, I don't want to say confused, but we have to start being flexible in what we refer to. So a bonding pair, or sorry, a double bond, a multiple bond, or a triple bond, even though there's technically two pairs of electrons in a double bond and three pairs of electrons in a triple bond, it's going to behave as a single thing. So that's going to also influence how we apply these things coming up. I would like you to build a table that looks something like this. Now I want you to understand that this is our basic table. We will have to expand this table in the next video, and I'll try and hint at where the expansion is going to happen. We have BP for bonding pair, so we're just going to have a list of the counts of bonding pairs. Lone pairs, well, for right now, we won't have any lone pairs. So you could fill in all the zeros right now. There will be no lone pairs in this video. And then the class. The class for me is not something that's particularly important, but they do have some commonality. I don't find it very helpful, and I find that there's a bunch of letters and stuff that just kind of get in the way, but I'll include it because the textbook does and most sources do. And then finally the shape. And the shape, I would suggest, if you can, have a place to draw a picture of the shape, but most importantly for us is going to be the name, and that's pretty much all I'm going to put in there, and the bond angles, because you are going to be asked to know the bond angles for these shapes. So the first one, two lone pairs, sorry I said two lone pairs, two bonding pairs and no lone pairs, and that's going to take the shape, or take the going to look like a central atom with two bonding pairs. So AX2, that's the class. Again, it doesn't really help us. It's more useful if you had actual chemical symbols in there, but so far. So if you put those bonding pairs as far away from each other as possible, they're going to go on opposite sides of the central atom, keeping in mind that this central atom has no lone pairs of electrons. They'll then have a 180-degree bond angle. So as far away from each other as possible, directly on opposite sides. A couple common examples of this. One would be beryllium hydride, and another one would be carbon dioxide. I only mention carbon dioxide at this point because carbon dioxide, as you'll notice, has a double bond. So we kind of have 4 bonding pairs of electrons, but there's 2 bonded groups. So we treat it as an AX2 type molecule, and it forms that kind of angle. We give that molecule the name of linear, and you'll notice that we're not being very creative with our names, but we are trying to be descriptive. Bond angle is 180 degrees, as I said. Moving on, we have 3 lone pairs, sorry, I did it again, 3 bonding pairs on our central atom and no lone pairs. And it looks like an AX3 central atom with 3 bonded pairs. If we were to look at that in 3 dimensions, and I realize that you're looking at something that's actually in 2 dimensions, so we're using clever shadowing and shading and things like that, but this one actually does still exist in 2 dimensions. It's a flat kind of thing. And if you were to look at it, bond angles would be 120 degrees. So if you were to lay an equilateral triangle around there, the bonded atoms, the peripheral atoms, would actually go into the corners of that triangle. An example of this would be boron trihydride. And if we were to give that thing a name, it is called trigonal planar. Trigonal because the groups form a triangle. Planar because it's in a flat plane. Okay, it is still a 2-dimensional thing. Bond angle is 120 degrees. Moving on. Now at this point we move into 3 dimensions, and I'm going to get it right. We have 4 bonding pairs, no lone pairs. And at that point, again, our class AX4, what it's going to look like this. We now, in order to get the things as far away from possible, we're going to go into the 3rd dimension. So now we're talking about depth. So now we have a bond that is coming out of the screen toward you, and I'm also going back into the screen behind you. At least that's what we're trying to represent using clever shading. The bond angles are 109.5 degrees. I know it's kind of a weird number, but that's as far away as we can get. It's better than 90 degrees if we were just to go into, say, the corners of a square. We can get 109, almost 110 degrees. Now, depending on what the groups are, they might equally share that and all be 109.5 degrees, or they might be somewhere in that range. We don't really care about that. Bond angle for us is going to be 109.5. Carbon tetrachloride, methane, CH4, CHCl4, things like that. Those are going to have this kind of shape. Once we start to try to draw them in 3 dimensions, you'll notice that the limitation we have as a flat page gets in the way. So we end up with a new notation. So you'll notice that on this one, there's the chlorine that's in the, say, in the foreground. There's a wedge. A triangular where the small point is at the carbon and the flat side is at the chlorine. That's trying to that wedge is trying to show that that molecule is coming out of the page toward you, or out of the screen toward you, and then the dashed wedge is trying to go back into the screen behind you. That's how we start to represent 3 dimensions on a flat piece of paper. It's based on, or if you put the carbon in the central of this geometric shape and put the chlorines in the points, you would end up with this mathematical geometric shape called a tetrahedron. So we borrow parts of that name and we call it a tetrahedral for our molecular shape. And we'll move on to the next one. What happens if I put another bonding pair in there? And I have 5 bonding pairs and no lone pairs. At that point, you can see the class. I'm not going to talk about it, but it starts to look like this. Now, the interesting thing about this is that I don't have as much symmetry as some of my other ones have. You'll notice that I have this up and down, let's call it the axial line, and then I have this equatorial one going around the center. And they actually have different bond angles. So going from if you look at the say the left-hand side, the up-down and the one pointing left, that forms a nice little T shape. And it's a perfect T shape in the sense that there's 90-degree bond angles. But going around the central, what we would call the equatorial plane, is 120 degrees. So it's kind of like that trigonal planar from a while ago in the middle, and then a linear one going up and down through that. That one, if you were looking at an example of that, phosphorus pentachloride, and again, no lone pairs on the central atom, and again, you'll see the wedge coming out of the page and the dashed wedge going back into the page, trying to represent 3 dimensions on a flat piece of paper. We give that thing the name trigonal bipyramidal because if you made the geometric shape, you would have a triangular based pyramid on the top and a triangular based pyramid on the bottom. So you've got 2 pyramids, bipyramidal, and they're triangular based, so that's your trigonal bipyramidal. And again, there's 2 bond angles we have to keep track of. This will be the one that when we start talking about putting lone pairs into the system, then we're going to have to be kind of careful because they're not all the same. Finally, for today, 6 bonding pairs, no lone pairs. AX6. Looks like this. This one does, we're back down to the symmetry. We're back to everything is exactly the same. And if you were to take that thing and twist it and turn it around, you would notice it would still look the same. We have 90-degree bond angles all the way around. So both from my up-down plane, or my up-down line, to the central, to the equatorial one, and around the equatorial. We also have 90-degree bond angles. As an example of a molecule that takes this shape, sulfur hexafluoride. And again, you'll notice a couple of wedges coming out and a couple of dashed wedges going back. And finally, if you were to make a geometric shape where the central atom, the sulfur, was in the middle and the fluorines formed the points, it would end up looking like this. And again, it's a mathematical geometric shape called an octahedron because it has 8 faces, but we call it an octahedral. Now, just quick little, don't get this mixed up, we have 6 bonded pairs and no lone pairs, but it's an octahedral. So 6 is not octa, of course, 8 is octa, but it's because of the number of faces that the geometric shape would have. And then again, the bond angle. Now, what we have to do moving forward, so what we have to do yet is, first of all, figure out what happens to the lone pairs. Where do we put the lone pairs? What if there's 1 lone pair? What if there's 2 lone pairs? Keeping in mind that lone pairs repel each other more than anything else repels. Secondly, how does it happen? It's one thing for us to say, and I said at the beginning, that what an orbital looks like might change as things change, but we then have to bring our quantum theory into this and be able to explain also molecular geometry using our theory. So that'll keep us busy for a day or so following this. But we'll sort out in class, we'll do some Lewis diagrams, get some use doing this, and then we'll add the layers as we need them. Talk to you then.